Okay, I would like to make a solution for this problem on the homework set 4 for anybody who's interested in this that's not taking the course. This is calculating the standard Gibbs free energy change and equilibrium constant for a redox reaction. So specifically, we're interested in the oxidation of the formate ion to carbon dioxide at room temperature and pH 7. So this gives us the temperature that we need in order to calculate the equilibrium constant. And also the pH 7 will tell us which midpoint to pick, midpoint potential to pick. We want a degree symbol with a little apostrophe, right, for the biological condition where pH is 7. Or as you may see if you're using Jim Allen's biophysical chemistry textbook, this is written as E with a subscript M, okay, the midpoint potential for this reaction or biological conditions. So we're only given this word problem, but I've pulled out the half reactions that you need. You may find this first one. It is the, I believe, 10th entry on the table that's posted on the biophysical chemistry website. But this is, of course, information you may Google also. And I did notice that there's a small discrepancy in the answer key because the answer of minus 0.414 volts from the entry above for the, let's see, formation of H2 from 2 protons and 2 electrons is minus 4.14 volts for the midpoint potential. So this does affect the answer slightly once you calculate the equilibrium constant, though it does not change the order of magnitude of the answer or, of course, the process that was posted in the key. Then we know that this is oxidation in water because it says the formate ion. I have had some questions, since this is a biophysical chemistry class, that maybe this is oxidation with NADH or anything like this. You can use the same process to calculate that one. You can just substitute this reaction, and of course your values will differ. But because we just have the ion itself, then we assume this is oxidation in water. Okay, so we use the reaction of an oxygen with 2 protons and 2 electrons to form a water molecule as our reduction reaction. Okay, so we're going to need to write one of these as an oxidation reaction, since these are the reduction reaction midpoint potentials. And remember that whenever you change the direction of a half reaction, you change the sign of E. So the first one is the one that I want to reverse because I am supposed to oxidize the formate ion to carbon dioxide. So we need to make this product into our reagent. So we will start with that we have the formate anion forming CO2 and protons and 2 electrons. So now that means that my midpoint potential is plus 409 volts. And I keep my same reduction reaction of an oxygen to H plus and to E minus to H2O with the same positive midpoint potential of plus 0.815. Now I want to sum these to get an overall reaction and the midpoint potential of the cell, right? Or delta E if you're considering this in terms of the book's notation. So we always need to make sure that totally the same number of electrons were transferred from one side to the other. But do notice that these midpoint potentials are intensive quantities. So you may multiply the entire equation by a coefficient so that the reaction is balanced when you consider the overall reaction. But you won't do this to the midpoint potential. Okay, also we cancel out the coefficients because we have 1 proton produced from the oxidation of formate. So totally, if we combine formate anion and 1/2 O2 and H plus, and we will get, remember the electrons cancel because they're both products and reagents, we will get CO2 and water. So we can therefore sum these midpoint potentials for a final of 1 1.224 volts. So this would be that E cell is 1.224 volts. Okay. So we can then calculate delta G as delta G equals minus NFE cell. So this one is the Faraday constant, and this one is the number of electrons transferred. So this will be minus 2 times, 9,600 or 96,485 coulombs per mole times 1.224 volts. And that is minus 236.2 kilojoules. So finally, we know that the equilibrium constant is related to delta G according to delta G equals RT, natural log of the equilibrium constant. So we can rearrange this to say that the equilibrium constant is exponential of negative delta G divided by RT. So this one will be exponential of minus negative 236.2 kilojoules. You want to make sure that you enter this one into your calculator as joules, or you want to use R, the gas constant, also in kilojoules, so 0.008314 kilojoules per mole Kelvin. And you want to put a set of brackets around these terms multiplied in the denominator in order to get the correct answer, order of operations wise, in your calculator. So let's see, I suppose I needed brackets here. All right. And so when you compute this one, you should get that the equilibrium constant is equal to 2.53 times 10 to the 41. Okay, so what that means is that there are way more products than reactants, right? We had a negative value for delta G and a positive value for the midpoint potential of the cell. Remember that when we have a positive value for the midpoint potential, that means that we have a driving force for the oxidation reaction. So delta G will be negative for this one, and we will form products. So we will have more CO2 and water in a huge fashion, 10 to the 41 times more than we have the formate ion and water, or oxygen and H+ hanging around. So make sure that you can also interpret the physical meaning of these expressions. I hope that helps. It doesn't differ too significantly from the key. I believe that in the homework key you have 1.229 for the E cell, which gives you minus 237.2 kilojoules per mole. And this one gives us 3.79 times 10 to the 41. So everything has the same order of magnitude, but some small numerical differences.